Okay, again, here's your definition of average rate of change of Y with respect to X. Now, in this case, it's M and T, but it's a rate. Okay, if you make $140 in 7 hours, well, you know how to find out how many dollars per hour that is. That's easy. Everybody knows how to do that, I think. Okay. It's unusual to find somebody that doesn't know how to calculate money. Okay, that's something that's important to keep. Speed. If you go 140 miles in 2 hours, that's 70 miles per hour, right? 70 miles divided, or 140 miles divided by 2 hours gives you 140 miles divided by 2 hours. 70 miles, it's 140 divided by 270, and miles divided by hours is miles per hour. Okay. So it's just that idea. And this is miles and this is hours, right? So in this case, M versus T. Write that out very well, didn't line it very well. But it's a change in M divided by the change in T, same idea. And why does that make sense? Well, let's look at it. From 630 down to 470. Okay, well, okay, on the interval 2-5. Change in M is 470 minus 630, which is 160, right? Negative 160. Change in T is 5 minus 2 equals 3. In other words, this minus this, this minus this, that's your change. So that's negative 160 miles, 3 hours. So negative 160 over 3, negative 53 1/3, meaning negative 160 miles over 3 hours. Negative 53 1/3 miles over hours, meaning miles per hour. That's how fast you're going. Is that reasonable? Now, if you're on an interstate, you're probably driving faster than that if you want to stay alive. Okay. But you might have made a stop, right? So you don't know what happened in between here and here, except that you covered this many miles in 3 hours. All right. Now you go to the others. And I'm not going to write out all the details, the calculations. This course open math videos show you that. You know, what we did in class last time shows you that. We've got to go on to other things. Okay, but you want to get this down. You want to understand in terms of an example involving miles and hours, or an example involving dollars and hours. Okay. And then look at some of the other examples. Doing the problems, design problems, you learn how to apply the thing and you learn the idea. Okay. So On the interval 5-9. Average rate is again change in M over change in T. And if you're doing these problems, you want to write them out. Okay, you want to write them out pretty much the way I do. You can adapt that to your own style, but you want to write out the details so you keep telling yourself what it is you're doing. That way you lock it in. Okay, so it's delta M over delta T, change in M over change in T. I believe the open math videos and the text use that notation. If they don't, well, pretty easy to understand. Instead of writing change in, I write a delta because it's shorter. So change in M between 5 and 9, we go from 470 to 240, so it's 240 minus 470 over 9 minus 5. That's going to be minus 170 miles. Well, no, yeah, minus 170 over 4. And that equals, is that right? Yeah. No, that's 230, isn't it? Okay. Too early in the morning for you and me. Okay. And that's negative 57 and a half. Meaning 57 and a half miles an hour. Going toward in the direction of decreasing mile markers. Okay, and then the third one on the interval 9-11. The average rate is delta M over delta T. You want to get used to writing stuff like this out. Equals 110 minus 240 over 11 minus 9. And that's negative 130 over 2, which is negative 65. Now in this interval, yeah, maybe didn't make a stop. This is 3 hours. This is 4 hours. Okay, stop for gas, stop to use the restroom, stop to walk around, retain your sanity. Okay. So you're averaging a little less speed on this interval and this interval. This is your last 2 hours. You just drive it straight. You average 65 miles an hour. There's some trucks. So you're not going to average 75. Okay. Make sense? Now, if you graph this, you have miles to go out to 11. So I'm going to scale my graph. I'm going to put a 16 out here. I'm going to put an 8 here, 4 here, 2 here, and there's 12, and we can fill in the rest. On miles, conveniently, I can use 640 here, because I can divide 640 in half and divide that in half and so forth, a whole lot of times. 64 is the power of 2. We have 320 here, 160 here, 80 would be here, 240 would be here. And we come up here, we have 480. And we have 560, and we have 400 here. So here we've got scale graph, and we can plot these things. 630 to go here with 2. So here is the point 632 to 630, and then 5, 470. And then 9, 240. 10, 11, 110. Okay. Now, this kind of almost a straight line from here to here. Of course, your average speeds are pretty close, 53 1/3, 57 1/2. Go a little faster here than you are here. If you draw a really accurate graph, this thing's going to be a little steep. And then this one is going to be even steeper because you go up to -65, okay? You can then get triangles. Okay. And let me these different colors, these triangles. This triangle up here, the green one. Its run goes from here to here. The run is 3. The rise is -160. Probably would have been better for me to draw the triangle here. Keep it where it is, -160. Okay, I'll write that down here where you can see it. Okay, that's the rise. This is the run. We divide the rise by the run, you get the slope. And you get -53 1/3. So calculating slope from this point to this point gives you the average rate of change. Now you want a meaning on that. You want to know it's miles over hours. Because that means -160 miles, because miles are measured on this axis over 3 hours. 3 hours are measured on this axis. So now this isn't something that's absolutely required, but actually it is in my students. So if you're in my class, you need to know that. You put a box around it here so you don't think that's the distance. You know, this is kind of a displacement. This is how far you go. And this is how far you go along these two lines. This isn't how far you go along 2 lines, that's the slope, that's the average rate of change. And you can do an average rate of change, you can do one of these triangles for each interval. The blue triangle matches up with the calculation we did for the second interval. You have -230 miles. That's the rise. The run is 4. Slope is rise over run. -230 over 4, -57 1/2. We do this. And on the last one, let's put the numbers. Got 2 here. You got -130 here. And you're going to have -65 here. So we can squeeze those numbers into the graph. It might be hard to read from where you're sitting. And it gets a little. Gets close to, got a label. The run here, but the run here is 4. I'll put the 4 here. I'll put the negative 230 here. So you see that on the graph, I've got all the numbers that I use to calculate everything. And I've got floats. And all the information is right here in the graph. Okay. It gives you a pretty complete picture of rate of change. Okay. An idea. Turn it on. Was I even recording before? Did I turn it off?
Turned it off just a minute ago.
Okay. Okay, I want to convince you that 5 to the 0 has to be 1. Now, usually you think that algebra courses would drill it into you that a number that was 0 powers 1 because you use it all the time. Okay. But one of those ideas, it's easy to lose. People want to tell me that 5 to 0 is 0, and that doesn't make any sense at all. And I'll show you why. Okay, what's 5 to the 3rd? Well, that's 5 times 5 times 5, which is 145. What's 5 to the 2nd? That's 25, right? And what's 5 to the 1st? Now, how many times this is this? 5 times this is this, 5 times this is this. And it keeps on going. We did 5 to the 4th, it's 625, 5 times 125, right? 5 to the 5th, 3125. Okay, and so forth. Okay, well. So every time we go down a power, we got to divide by 5, right? Well, if we go down one more power, what power we got? We got 0 power, right? 5 to the 0. Well, it's not even equal to 5. There are no 5s there. So we don't really have anything right here. But we know that it's going to have to be 1/5 of this, right? What's 1/5 of 5? 1. Okay. Okay, well, we can keep going. What's 5 to the negative 1? Okay, well, let's talk. I think everybody will probably see the idea, but let's make sure. Okay, so 5 to the negative 1, well, we got to divide the last power by 5. The last power out is 5 to 0, that's 1, so it's got to be 1 divided by 5, right? And then five to the negative 2 has got to be 1/5 divided by 5, which is 1/5 times 1/5, which is 1/25. Okay. But really, we don't care that much about the numbers. And actually going to be 1/125. You know, you're just going to have these numbers here in the denominator. Every time you divide by 5, your denominator is going to get that much bigger. It's easier to write 5 to the negative 2 is 1/5 squared. If we divide 1/5 by 5, that's what you're gonna get. Okay, that's right here, 1/5 squared, right? And that keeps on going there. Etc. 5 and -3 is going to be 1/5 to the third. I could write that, that's 1/25, this is 1/125. And you just keep on going, okay? So if I convince you that powers have to act that way. Okay, well, you got a homework assignment on it, okay? It's an Algebra 1 level assignment on negative and zero exponents, okay? That shouldn't cause you much trouble. But make sure you get it done. Okay. We got toolkit functions. The toolkit squared function or quadratic function y equals x squared. We can easily make a table of y equals x squared versus x, and we can make a graph. Very easy. I use numbers. Where I differ from open math is I really want people to understand the numbers, not punch them into a calculator. Open math shows you how to do these, and I punch all the numbers into a calculator and get decimal rather than fractions. Well, decimals are important and they're easy to understand. It's important to understand fractions. And I just emphasize it. So I think you understand it better. You understand it in terms of fractions. So the x values I always use, unless somehow we can't calculate them without a calculator, are -2, -1, -1/2, 0, 1/2, 1, 2. Now, open math is fine if you just punch it in. Matter of fact, open math doesn't even want fractions for the answers to these things. It wants decimals. Okay, I disagree, but these people know stuff too. So, matter of taste, I guess. Again, I want to emphasize that we want to understand the numbers. We want to understand why the functions have the shapes they do, and you don't understand that if you use the calculator. Okay, so x equals what? Fill out this table for me. I'll start it for you. If x equals 2, then what's y going to be? Show me with the fingers. It'll be 4, right? Because y is x squared. If you square 2, you get 4. Okay. So go ahead and fill in the rest of the table using rational numbers, fractions rather than decimals. X is -2, y is x squared. So we're going to get the whole -2 gets squared, meaning that this is -2 times -2. Well, 2 times 2 is 4. 2 negatives multiplied give you a positive, right? So a lot of times I'll see a negative here. In a typical class, maybe half the class will write that as -4. So if you wrote -4, you get a lot of company, but understand what you're doing, okay? When you square a number, you multiply it by itself. I'll also comment at this point that you write it like this: -2 squared. The order of operations says that you do the exponent to 2, and you don't do the exponent to the negative. So all you're doing is you're squaring 2 and then putting a negative in front of it. If you want to square -2, you write it like this. You want to be careful about that, especially if you're using a calculator. If you got a negative quantity and you want to square it, Make sure you square on the negative as well as the rest of it, okay? Okay, so -1. Okay, what's -1/2 squared? -1/2 times -1/2. What's 1/2 times 1/2? You multiply the numerators, you get 1, right? And you multiply the denominators, you get 4. That's 1/4. Think about it. You got $1, you cut it in half. You got 50 cents. Take half of that. You got a quarter. Quarter of $1, right? You square a half, you get a quarter. Half of a half is 1/4. That's what it means. So you really want to think about that. You really want to make sure you understand that, because you do need to understand fractions. Okay, well, 0 squared. 0 times 0, 0. 1/2 squared. Is again 1/4. 1 squared is 1. Okay, so there we have. Table. Can we graph that? Can you sketch me a graph? How long was that delay in seconds? Good heavens. Come on, Zoom. Well, I appreciate you. Okay. Sometimes I wish a little more responsive. Okay, I'm going to draw the graph. Y equals X squared. I'm going to put 2 out here, and I'm going to put -2 here. There's no point in putting any numbers bigger than 2 or less than -2, because your X values go from -2 to 2. Okay. And then I divide this interval in half. And there's 1. Then I divide this interval in half, and there's 1/2, 1/2. Pushing aside their negative. Okay, then what am I going to need for Y? Well, my numbers go from 0 to 4. Now, in terms of the language, my domain goes from -2 to 2. My range goes from 0 to 4. Now, this function is defined well beyond this range, but it's going to have the same shape no matter what your domain and range are. Okay. So put 4 up here. I'll put 2 here. I'll put 1 here. I'll put 3 here. Now, I'm also going to need numbers like, well, I'm going to need 1/4, right? How am I going to get 1/4? Well, I cut 1 in half, that gives me 1/2. And I cut that in half, and I've got 1/4. And 4 of these, 1, 2, 3, 4, make up this one, right? So there's where 1/4 is. And 1/2, of course, is halfway between 0 and 1. Now that I've got all these, they're both axes labeled, got all these labels. I got -2, 4. So here's -2. Here's 4. Here's the line X equals -2. And here's the line Y equals 4. They intersect at this point. Then -1, 1. I need the line X equals -1. And the line Y equals 1. And they meet here. So this point is on the graph. Then line where x equals -1/2. And where y equals 1/4. So here is a point. Now do the same over here. I'm not going to be that meticulous on this side. But I'm going to be using the same y values because this thing is symmetric. You have the same y values from one side of 0 as you have on the other, and it's easy to see. I have the same numbers on this side that I have on this side. It's just a negative. Okay. And when you square the negative of one of the numbers, you get the same thing you do when you square the number itself. Okay, so I get these points. And of course, I get 0, 0. And now I can draw a pretty good approximation of the curve. And if you're in my section, it shows you how to draw an accurate curve. Because so far, all I've had to do is just slop down something that looks parabolic. Now we can draw a pretty good parabolic curve if we make sure that we subdivide in half as accurately as we can. And the 2 is as far on this side as -2 is on this side. Okay. So. Now that's not perfect. It's a little lopsided to the left. It's not too bad. If you try to draw one, I wouldn't get draftsman tools out to do it. But of course, I mean, if you really want to see a pretty graph, that's okay. You're just trying to draw one of these graphs for reference to make some estimates and to understand some things about it. You should be able to make that table and draw the graph in a minute. If you want a really accurate graph, maybe 3 or 4 minutes. But you should be able to slot that graph down in no time. Okay. Now, what can we do with this graph? Well, here's 3 halves. Take your sketch. Draw your vertical line for x equals 3 halves. You come over here and see where it hits the y-axis. Don't take mine because mine isn't all that accurate. Yours won't be either, but make your own estimate. Okay, let me show you a little more. Okay. On my graph, if I go up here now, this is a little too far to the left, it should have been a little further to the right. Anybody that had a better estimate. But if I take this as the point of my graph, come over here. What's that look like? It looks like about 1.8, 1.9. Okay. Okay, so. Here's a good color there. Y is about 1.9. So my estimate x equals 3 halves. Y is approximately 1.9. Okay, well, turns out that's not a great estimate. Okay. Not bad, it's not great. Check. If X is 3/2, if you square 3/2, you get 9/4. 3/2 times 3/2, 3 times 3 over 2 times 2, 9/4. Which is 2.25. So my estimate was off. And I did draw a perfect graph. And I did draw a perfect projection line. This line is a little too far to the left. If I'd have put it a little further to the right, I'd have had a higher estimate. Still, a good graph can get you fairly close. Come off by 10, 15%. Okay. It's not a terrible estimate. And of course, it's something you can easily calculate. All right. Things get a little noisy in the hall. Okay. Now, other functions. Okay, y equals 1/x. We plug the values of x in, we get 1/-2, which is -1/2. 1/-1 is -1. 1 divided by -1/2 is 1 times -2/1, which is -2. Now you divide by fraction. 1/0. Somebody want to tell me what 1/0 is? Okay, so we can't divide by 0. It's undefined. If you have that calculation in open math, does not exist, DNE. They're probably to say that. Well, then. One divided by 1/2, well, there, you can count the 1 by 1/2. Okay, a half and another half gives you 1. It takes 2 1/2 to make 1. That's what we mean, divide 1 by 1/2. And that's an insight you don't get if you do your calculations by calculator. You don't understand how these things work. And this one gives you 1/1, which is 1, and this is 1/2, which is just that old 1/2. So what's our graph look like? Running real short on time here. We're gonna have to squeeze it in right here. We only need numbers from -2 to 2 on the x and also on the y. Biggest number we get is 2. Small, the least number we get is -2. If we plot the points, -2, -1/2. Well, okay, so we got 1 here. Here's 1/2. Here's -1/2. Here's 1/2. Oh, actually, no. I don't know. Forget those. But okay. So let's see. My -2 is kind of in the way here. But right there is my -2, -1/2. Then my -1, -1 Well, x is -1, y is -1, that's gonna be here. And then -1/2, -2 is gonna be down here. And that's gonna give us a curve that looks something like this. Now it's familiar. If you've been in my class, it's familiar if you've seen it before, if you've already seen it in Jason's class. So there's the curve. One thing we don't do is we don't connect this point to this point. If we connect this point to this point, we've got to pass through the y-axis. If we pass through the y-axis, we pass through a point where x is 0. That means 1/0 would have to equal that. And 1/0 isn't defined. We can't pass through a point where the graph is undefined. Okay? We can't pass through a point where the x value is not in the domain of the function. All right. So there we got it. We're out of time. We also have the exponential function. I'll give you the formula for the exponential function. Y equals 2 to the x. You can't calculate this for x equals 1/2. Okay, you can punch it into the calculator, but the calculator is not going to tell you exactly what it is, because nobody can write down exactly what it is in decimal form because it never ends. It never repeats, it never ends. There's no way to write it down, there's no way to calculate. There is a way to calculate it, to approximate it. You learn that in the second semester of a calculus course, so you don't want to mess with it here. Okay. So talk about that a little bit next time. But for the exponential function, I'm going to make the table. I'm just going to use -2, -1, 0, 1, 2, because you can't calculate it. That x equals 1/2 or -1/2. You don't have a clue how to calculate it. Okay. You won't have a clue how to calculate it unless you take a couple of semesters of calculus. Okay. So unless you want to do calculus in here, don't even try to calculate 2 to the 1/2. You can draw a good graph and estimate 2 to the 1/2 power. And you get a pretty good estimate because the graph is pretty smooth. Okay. This graph. Kind of looks like this. That graph's real important for a lot of things. Models how fast bacteria grow in your food. Models how much money you have if you invest a certain amount of money at a fixed interest rate. Show you how your money grows. Show you how inflation grows. That's not so good. Okay. Make sense? Maybe not, but that's what this function is good for. Plus, among other things, that function kind of governs the whole universe. Okay. Everything from oscillations to exponential growth to everything else. So it's, I would say, the most powerful function in the universe, even though it isn't even a power function. Okay. You know, this thing is supposed to turn